further ado, once again, thank you. Diamagnetically levitated robots, Joseph and Yuzheng. Thank you.
Okay, hello everybody. Today Joseph and I will talk about the diamagnetically levitated micro robot. Firstly, I will go through our the knowledge we have learned here in the past lectures. Diamagnetic materials has no net magnetic moment when there's no external applied field. And then if we do apply a field, the magnetization of the material will go anti-parallel to the external applied field. And when we remove that field, it will go no moment anymore. So usually for the non-magnetic material, it has a very low susceptibility, which is the 5. So this curve compared to the ferromagnetic and paramagnetic is very lower number. Okay. I told you I want to levitate some objects. So in order to do that, we need some force or sometimes torque. So in order to generate the force, based on this equation, we need the magnetization in the material, of course, and then also we need the B field gradient. So we can get this B field gradient by a simple permanent magnet. It's very easy, just by changing distance from this magnet. And also I have this magnetic material. It's a piece of copper, so very simple. If I put it on top, you can see I cannot feel any force or no levitation. But you may ask why. It should work here. So two reasons. The first one is this magnet is not strong enough. The second one is this thing is too heavy, too big. And in order to levitate some objects, you need to figure this out. Okay. Firstly, we want to use the graphite, which has almost the highest magnetic susceptibility as room temperature. And also, we also have some DFED magnets, which also the most strong magnets we can get. Okay. There's a theoretical problem. A guy called Samuel Earnshaw in 1842 proposed a theory that a collection of the point charge cannot be maintained in a stable stationary configuration solely by a electrostatic interaction of either charges. Okay, this theory is firstly talk about the electrostatic field, but it can also be applied to the magnetic field. So that means our experiments cannot be done if it's not real. Then it's become possible. Somebody expand this theory and put more possibility for this situation. That is, if we include some diamagnetic material in this setup, and the interaction of the repulsion force and the attractive force can be balanced. So there's something the objects can be levitated. This is a big picture of our setup. This is a big reactive magnet with alternatively north pole and south pole. We managed to assemble them. This is a piece of graphite. It's small size and very light and has very high phi number. Actually, I can show you this. It's too small. Do you want to come here? This is we use a circle magnet instead of the square one, cubic one, same thing. And we have a piece of the graphite. very lightweight. Okay, as you can see, there's a very tiny gap. I would say less than 1 millimeter. And it can float on top of it. And but if I touch it by
one thing to note is that we'll always want to go back to the position where it's at a 45-degree angle of the other magnets, usually cubes, case disc.
Does it have anything to do with the gap between those?
Yeah.
Partially because the field's going to be strongest at the base of the magnets, so it's going to magnetize the part of the graphite above that the most. It's going to want to be leveled out, evenly distributed, and the gap is where the field's the weakest. So it makes a little bit of a weld, a bit of a saddle, and it will always want to sit in this position.
Yeah, the magnetization of the material will find a place to get it equally distributed in this material. Okay, so I think in the middle is it seems to equally distributed the field, but in fact I think in the middle of this magnet will be more equally uniform. The field will have it's for sky. I will go later. Okay. And can we play the video? I think this is it. We will have another demo. Yeah, over.
So do you want us to stay down here?
If you want.
You don't have to. I'll talk about mine if you want. You can. We have 3 other minor displays to show you.
Yeah.
This will show the. This one's a 3x3 array. So, and since the magnet or the graphite is larger in this case, it doesn't really want to stay over the crosses of the 4x4 arrays. It'll stay more towards the middle. Again, it wants to do its best to evenly distribute the magnetic field that's being generated by the magnets. And this is showing that it can handle some mass on top of it and still go back into its position.
I will choose several part. I will make it straight. Okay. Look at these several three circles. The only can find this crossing point, which is the most stable point. This is a square one. And what is the you have something. What if we have some weird shape? It's gonna stay also as the crossing point, but along its longest axis.
As you can tell on the little graphic on the right side there, you see how it's going to kind of form an arc, the field coming out of the north angle into the south. And doing this in the array, think of it as a 2x2, you can see how it kind of forms little arcways for the tips of the points of the graphite to sit in as it sits on top of the lowest point at the cross of all 4. Right. So we showed you that graphite can float on top of an array of magnets, but it's not as useful as it could be. What if we flipped it though? Right here we have a large graphite sheet with a small array of magnets, again in the same orientation, north, south, north, south. The carver, as he showed earlier, is not really relevant to what we're showing today, but it's helpful. Now, this means that the magnet's not really going to sit in one spot. Now that the field is, now that the array is smaller than the actual graphite, it doesn't want to stay still. It wants to slide around, move around, or wherever. And right here, I can show you. This is a large piece of graphite with a small 3x3 array. As you can see, it still floats and likes to wiggle around. It has no control and have boundaries on it to keep it from flying off. It has to be very level. Any movement is going to knock it off.
Actually, that's the same idea as this magnet, but much smaller and glued together.
Yeah.
So the thing that floating, you just flip everything upside down.
Yeah. Now,
How
the
big are
main,
the magnets?
Huh?
Hmm?
How big are the magnets?
I think they're 1 by 1 millimeter.
1 by 1, 9 of the 3 by 3 array.
Yeah. Where this comes in really handy and what makes it more important is if you have a printed circuit board, you can put it underneath. And depending on the direction that you send the current towards, you can actually control what your robot does on top of the graphite. This is where micro robots actually comes into where there's a purpose other than just randomly floating around. We do have a demo on this. Ours is not going to be nearly as precise or accurate as those with a printed circuit board, but we can at least give you an idea of how it can work. This graphite right here has a little bit of a bowl shape to it. That's so that this magnet should most always return to a rest position just to keep it easier for our experiment's sake. A better version, like I said, would have it where the printed circuit board would be controlling where it goes. Would anybody like to see the magnet move? Anybody?
Just make sure to not touch
Touch,
the table.
yeah, touch the exposed part of the yoke.
Yeah.
Let me see if I can do this. There you go. Look.
Okay. Release that.
Oh, there's a.
Okay, yeah.
So we're seeing about 1 amp through each of these wires. They're small wires, and of course the force is going to depend on the length of the wire and the amps going through it. The design for the circuit board that I used uses transistors. That way I can send my current down the chosen path using something like a DAD board. I can send voltage to one of the transistors and making that path the only closed path with the rest open, so all the current will go through that path. We're having a little bit of issues getting the power supply to work well with that configuration. It kept giving us a compliance error. So that's why we're doing it with the, just connecting it by hand right now. But this would be something very similar to when they use the printed circuit board. They would have to have a really nice function generator in order to control where the robot goes. And by doing this, they can have it perform various tasks.
Okay, we already show you we can levitate something, a piece of graphite. Then we can levitate a piece of several small magnets. But we are talking about the micro robots. And right now we can control something that let it move. Right? But how to move, what's the differences between things can move by controlled or the micro robots? That means we need to attach some called end effector to that piece of to that small magnet. The end effector is a very general term. That means there's some device can interact with the environment. I will show some most advanced technology that people are working on.
This is from the SRI International Lab, and they're doing most of the work with this. Almost all the information we found is through their resources. But they're doing some amazing things where you can see how fast they're moving it. And just, you can go up to surfaces, and you can see the printed circuit board's design right there on that green one. This one even can go on inclines, which I found really impressive that they're able to get to work. And a whole bunch of them working at the same time very rapidly. All it requires is just better circuitry, better printed circuit board.
This is what we call the end effector. You can do something. You can assemble. I don't know what thing it is, but do something.
So basically, using something like this, you can have a whole bunch of little robots performing a whole bunch of little tasks to do something bigger. And even the person that helped us with this project, because I point out the similarities between that and the cartoon movie Big Hero 6. And it's something along those lines. Of course, it has to be attached to the graphite underneath it, and then the board moves it, but with the right program and the right circuitry, you can make them do a surprising amount of work on their own. And that's it. You guys can play with it if you want. It's there, it's very hands-on. I brought the bigger piece right here of graphite to show that the small one will nicely sit in that saddle, but the large one will just kind of want to slide off. It doesn't really stay there very well because it's too large and thick in the saddle being created by the magnetic fields.
So with the controllable version, is the robot a piece of graphite or is it a magnet?
It's an array of magnets.
So in that case, the robot's the magnet.
Yeah.
While here the robot's the graphite is floating.
Well, that what I just showed you is, yeah, right here, the magnet's the thing that's floating.
Okay.
It's a little 3x3 9 magnets.
Okay.
And so you can see how it bounces around so easily. That's why it's in that bowl shape, to keep it so that's
So
more stable.
how did the people who are using them in applications minimize that bounce? Like, how did they, because you put it in a
They have
place
to
and then
have
it
the
bounces.
currents going through the printed circuit board and hold it in place.
Okay.
They have to physically,
So
like you saw that one.
physically,
where
like, align it
you
all
have to,
throughout.
yeah. Like I tried doing some seminar, it's very difficult with my dad board, and I couldn't send enough current through it. But like having one current go another direction and the other one go another direction,
it keeps
hold
it
it in
centered.
between. But that's really what they need to be doing. But like I said, it's got to be good program to run it and good circuitry to actually contain it. But regardless, we found it's a very interesting topic, and I'd like to see what kind of future uses it has as it gets more advanced.
So it does not need to consume energy or, let's say, battery to just lift it up.
No
So
need.
Yeah, it's all
how
it's all-
about if I want to move them to other position?
Yeah, you need to
That's-
provide some energy.
That's what the current wire is for, is to push it. Basically, when it's sitting on this one, it's almost frictionless, as long as it's not like leaning and touching the graphite below it, which means it's going to move wherever energy pushes it, wind, bump to the table, which is why you just put the little current carrying wire underneath it, it will give the push it needs.
So will the movement generate heat and degrade the magnetic performance? I mean, because they need to move and they need to cut the B field.
It means generate some small current in the
Oh,
magnet
yeah,
or
yeah.
something.
Yeah.
We assume it's very small.
That was what the copper we saw earlier is what they used that for, to prevent that.
Thank you.
Anybody else? Anybody want to touch it?
You do it. You touch it.
I found it just really fun. Just like you said, no matter what you do, whichever well it's over, it will conform to that position. And like I personally was the one that sanded down this one right here that has the borders on it. And while I wish I could make it more, concave, so it would have held its position better, it's still really interesting seeing how, if you held it right, how fast it zoomed across, just because zero friction, kind of like the maglev trains. Reduction, friction, loss of movement.
Yeah, why don't they do that with maglev trains?
It's similar, but you can see how small the magnet has to be. So the maglev train, the weight would really just be too much, but that's why you have to have electromagnetic force that much more into it.
What was the diamagnetic material you guys were using?
The
This is
graphite?
early
The graphite.
Graphite, yeah.
It's
The
man-made
the
carbon.
advantage-
I'm sorry, I was just saying it's a man-made carbon.
The advantage of this thing is it can, it can levitate by itself, no extra energy. But for your train or something, it requires some electric to get it levitated. Okay, that's it. Thank you.
Yeah. All right, thank you. All right, so that concludes the demos for today. We'll see you next Tuesday.